In this video, we'll talk about evolution of sets of numbers. So the first number discovered by men is the counting number, also called the natural number. Let's represent the sets of numbers using Venn diagram, and let's represent it this oval here. And the notation for our counting number or natural number is this one. Natural number is a number containing the set 1, 2, 3, 4, 5, and the list will go on to infinity. This set of numbers is called natural, perhaps because even animals can count their young using this number. That's why it's called natural number. The next is we only added one element to the natural number, which is 0. Perhaps during this time, people discovered losing something and meaning having nothing. So this is just one inclusion in the set, and this is now called the whole number. Let's denote the whole number as n with 0. So this is the set of whole number contains 0, and the rest is counting numbers. Next discovery by man is the integers. Perhaps during this time, people already learned how to make business with one another, and then they found out about having debt or something, or they owe to someone and they have negative assets or something. So this one is called the integers. Integers, denoted by Z, is the set of numbers containing, of course, it contains the natural number or the whole number, and this will go on to infinity to the right. And then we also have the negative of the counting number to -3, and the list will go on to -infinity to the left. So this is the integer. Next is people start to discover the fraction of something. So this is now the list of fraction or set of fractions, which is called the rational number. The rational number is denoted by Q. We cannot list the elements of this number, but we can express it into a symbol, like it is a form of m over n, meaning it is a ratio of integers. M is an integer and n is the integer, and we denote it like this, or we write it like this. M and n are element, this one, or belongs to the integers. Of course, our n must not be 0, or else it's undefined. So you can have any m like -2, -3, or all positive, or any positive number like 5, and n could be any negative number, positive number. As long as it's not 0, then it will form a ratio like 2/3, 5/6, or anything like that. So this is the rational number. Okay, this is 0, 1, 2, 3, and this will go on forever. to the right, and we have negative number here. So our increments is represented by the integers. Go on to the right. Now, these are our integers. 1, 2, 3. It's countable. If we go to rational numbers, say consider this interval 0 to 1, then rational numbers are fractions. Say here in the middle, we have 1/2. If you want to go here, which is a middle of the middle, which is 1/4. And if you want to divide this into 3, you get 1/3, 2/3, 2/5, and so there are infinitely many, like it's uncountable. Even if you pick a very small interval here, there's still infinitely many, or they're uncountable. There's so many rational numbers in this interval, no matter how small it is. Next is the irrational number. Now, the irrational number is not a rational number. Because what is a rational number? A rational number can be expressed not only fraction, but it can also be expressed into decimals. If we express this into decimals, it could be a terminating decimal, or a repeating decimal. So when you say terminating decimal, that's decimal that stops. For example, 0.352. It stops. No matter how long it is, as long as it stops, it's terminating. The repeating decimals are decimals that repeats. For example, 4.2323, like that. This is the repeating decimal. And any form of decimals like this is a rational number. Now, we have another set of numbers which is not repeating and not terminating. And this is discovered by Hippasus. Hippasus belongs to the Pythagorean group, which is founded by Pythagoras, and he was killed because of his discovery that there are numbers beyond the rational numbers, because the Pythagorean during that time believed that all numbers can be expressed as ratio of two integers, but they were wrong and they were disappointed of this discovery. That's why they killed Hippasus. And let's denote this set of number as, let's put it here, doesn't have common element as the rational number, and is denoted by q prime. So let's write it here, q prime. But we cannot express it in this way, the q prime, but if you express this into decimals, this is the opposite of the terminating and the repeating. So this is terminating or repeating. This one is opposite is non-terminating, and it's the same, non-terminating and non-repeating. So these are numbers like square root of 2. In fact, this is the number that Hippasus was working on, a discovery that cannot be expressed in fraction. Square root of 5, like the pi. This one pi doesn't stop and doesn't repeat. The exponential number, and a lot more constants that are irrational number. This set of number completes the number line. So if you combine all this, by the way, as I said, the rational number and irrational number has no common element. So in sets, we denote it like this, meaning they are empty. They're away from each other. And if you combine all these two sets of numbers, we know then the number which is commonly used in calculus, the real numbers. Okay, let's write it here. We have the set of real numbers. This is the set of real numbers. And the set of real numbers is just simply the union of the rational and the irrational number. There you go. So if you look at the real number line from 0 to 1, for example, we already talked about the irrational number. There are infinitely many points here, but there are still holes. There's still holes in it. If you want to enlarge this part here, this line here, for example, this is our 1, and we have to enlarge it. There's still holes in here because this contains the terminating and repeating, and the holes, the gap between the two rational numbers are the irrational. There you go. And the irrational completes the line, and we have now a continuum numbers, which is called the real number. So if you want to find the number next to 1, for example, you will say, okay, I will get 0.999. That's very close to 1, but still you can still find 0.9999 and 1, for example, and the list continues. So you will say perhaps next to 1 is 0.999, and this will go on forever, but actually that is just equal to 1. So you cannot really get the number next to a particular number. Instead, in mathematics, we just simply get a very small interval, which we denote as delta or epsilon, to get the number which is the neighborhood of a number. Say for example 1, the neighborhood of 1 could be the number very close to it. Okay. Next of the real numbers is complex number. So this is interesting because we have some equations like x squared plus 1 equals 0. Now in here, if you want to solve it, x squared equals -1. Now no matter how far you find your x here, there's no such x that will equal to -1. If your x, say for example, x is -1, and the square of -1 is 1. If your x is 1, the square of 1 is 1. So there's no way you can get a -1 for a solution of this equation. And the only way to get it is to let your x equals to square root of -1. And this number is no longer a real number. So what is this number? Now we denote this as imaginary number. This is denoted as the I, or simply the imaginary number. So aside from the real number here, we have now the extra number outside the real number, which is the imaginary number. And if you combine the real number and the imaginary number, this is now what we call the complex number. And the complex number contains the real number and the imaginary number. So the elements of this complex number, for example, is 2 plus 3i, could be negative, could be any of the real number here, could be pi or something, or like that. As long as it's real number here and there's an imaginary part in there.